Number 6. Nice. Let's get this done. Let's get this done. Let's do it. Let's do it. Do it. Right, where are we? Alpha, beta, and gamma are types of ionizing radiation. Okay, we know that. State 2 ways which gamma radiation is different from alpha. Gosh, okay. Gamma is not a particle, it's a wave. It's an EM wave. Alright, remember that from P1? EM wave. It's not no mass. It's massless. Okay. Alpha is a particle. It's made of stuff. It's a helium nuclei, isn't it? It's a helium 2+, right? 2 protons, 2 neutrons. Okay, it's a particle, and that's a wave. Other things we could talk about: gamma ray penetrates. Gamma is very penetrating, we could say. Alpha is not penetrating. It'll be stopped by, I don't know, a bit of paper or something like that. Okay. Gamma is not very ionizing. It's a weak at ionizing. Alpha is strong at ionizing. In other words, it'll spell that with an S and that with a Z. Right? It is. I don't know. Right. So we could have any of these two. That would get me 2 marks. Okay, it's only 2 marks. That would get me 2 marks, or that would get me 2 marks. Okay. Easy peasy stuff. Just recording facts. Right. Let's have a look. Complete the sentence by putting a kiss in the box next to your answer. A beta particle is emitted by... Come on, they're taking the mic. An alpha particle, that's rubbish. A fusion particle. A fusion... And they're taking the Michael. No. A gamma ray, huh? Okay, an unstable nucleus. Okay, remember nucleuses, they've got full of protons and neutrons, yeah? To get more stable, a proton can convert to a neutron, plus an electron, plus some other bits and bobs, okay? That's in P3, by the way. So, but an unstable nucleus, okay? Move on. Right. Complete the sentence by putting a kiss in the box next to your answer. A beta particle has an identical charge to... What do you mean? It's an electron, because a beta particle, or a beta negative particle, is an electron. It's an electron that's just like flying really fast, okay? Easy peasy. Good. Explain how an atom becomes ionized by radiation. Right, if something's going to be ionized, it's either going to lose an electron, or it is going to gain an electron. Okay, so let's put this into an answer that makes sense. Atoms are ionized. I'm going to use a Z, I like that way. If they lose an electron or gain an electron, okay. We could also mention, because what's actually happening is, we could say that the radioactivity is knocking. Oh, I spelt that wrong, didn't I? Knocking an electron out of the atom, or something like that. Okay. Now, Mark's scheme says an explanation involving electrons for 1 mark, because it's electrons, it's a key word, isn't it? Yeah. Is, are lost, or whatever, or gained. Okay, and that's the 2nd mark. So as long as you're putting this into a sentence, the atoms are ionized if they lose an electron or gain an electron. Hang on a second, but in the mark scheme, it doesn't mention anything about what's doing the removing or releasing. So let's say that atoms are ionized if they lose radiation can remove electrons. I don't know, something like that, but that's what the mark scheme says, okay? Not a very good question, that one. Alright, let's move on. Oh my gosh! What is this? Okay, someone's got a camera from the 1930s. That's when I was born. The removable lens of this old camera has 4 pieces of glass in it. One of the pieces of the glass is radioactive, What the, huh? Its surface is covered with a thin layer of magnesium fluoride. Radioactive isotopes in the glass emit alpha, beta and gamma in all directions. Okay. A scientist removed the lens from the camera. She measures the radiation coming from the back, the front and the side. The amount of radiation is different in each direction. Okay, so we've got this pretty picture here. We've got loads of radiation coming out here. We've got like some coming out here and some coming out here. Right. First of all, let's talk about this lens. Right. I had to ask a colleague about what these lenses are. Okay. So apparently this lens here, okay, is radioactive. Its surface though is covered in this material, which is what's it called? Magnesium fluoride. Would that be MgF2? Would it? No, ask your chemistry teacher, right? Now I'm guessing that any alpha particles will not be able to get past that layer because that layer contains metal ions. Yeah, that's my guess. Okay, but I reckon that the beta and I reckon that the gamma can actually get through. Okay, with me so far? So I reckon that the alpha and the beta can get through here. Okay, so that's all that. I reckon that any betas that are coming this way will get absorbed by the glass. So I think the only thing coming out the side here, at the back here, look, is gamma. I reckon, well I know, that any betas will be blocked by this aluminium. And so the only radiation getting through here is gamma. Let's straighten that up. Are we happy with that, children? Let's move that back. Okay. That's better. Right, so first of all you will notice a slight difference here and a slight difference here. Now I know that background radiation, the background radiation varies. We know this, don't we? So that would account for the slight difference in these two results, okay? It's good, good, good. Let's do the question. Right. Oh my gosh, let's do this. Let's do it this way. There we go. Let's do it this way. There's lots of space there, but we're not going to use it all. Okay. Let's move this out of the way. Let's get it focused. Right. Okay. So how are we going to approach this question? I would approach it like this. I would talk about the back of the camera, then the front of the camera, and then the side of the camera in any order. Right, I'm going to start with, did I say the back? Okay, so the back of the camera. Let's say the back of the camera. Let's say that, I don't know. Straight away, let's write no alpha particles. Can pass out of the lens. Okay, they're being blocked straight away. Okay, let's say that beta and gamma radiation is emitted. Let us further say that both beta and gamma are detected, and that makes up the 720 becquerel. Okay, I reckon that's a reasonable start. Okay, let's have a look at the front. Okay, let's go back to this a sec. I've just had a thought. Right, beta particles can actually travel through air, can't they? They can go about 30 centimetres or so. So, and both gamma. So we could say beta can travel through air for about 30 centimetres. So here we go. Looking back at the diagram, the beta particles would have no problem being detected. Alright? Good. Oh, let's get comfortable. Right, the front. Okay. The beta particles, remember, the beta particles can't get through these bits of glass. Okay? So only the gamma's getting through. So we can say the beta particles are being, use a keyword, I like keywords, absorbed by the glass. The gamma rays pass easily through the glass to the whatever the detector is, and that's reading 110 becquerel. That's 110 radiations per second. Okay, easy peasy. The side. Okay, remember the side, right? We've got this thick aluminium, right? The beta particles are not going to get through there, but the gamma will, right? Gamma requires quite a lot of material to stop it. So, what could we say here? So the side, the beta particles are absorbed by the thick aluminium. The gamma rays pass through easily. Okay, and I put an aside here, gamma rays can be stopped by thick lead. Okay, remember lead is really dense, right? Lead, volume for volume, is much heavier than much heavier than aluminium. Okay, so that's why it can be stopped. Okay, now then, looking at mark scheme. All these ideas are the ones that they want you to talk about. Okay, oh gosh. Including some. There's lots more we could say. Some of the here we go. Some of the gamma rays are going to be absorbed by the aluminium, right? Just by probability, but not a lot. They'll just go straight through like it's not there. And one other thing we could actually say, if we were going to try and prove we're being smart, and I've actually used up all my space here. Oh gosh, here we go. If we wanted to be smart, we could say something like this about these two differences here, right? That these two differences are most likely due to variations in the background radiation. We could say that, okay? I would say that this, it scores at least a 5. If you're saying something like at least a 5, I reckon it tips into the 6. The problem with these 6 mark questions is that they're quite difficult to mark, and they do get moderated by the guys at the who do all this marking. So, okay, I'm going to leave it there. Enjoy. Bye-bye. Bye.